Molecules are formed when two or more atoms form a bond that holds them together. We can have molecules that are very small, like oxygen, or we can have molecules that are quite large, such as most proteins, lipids, nucleic acids. All types of biological molecules tend to be quite large. There are three types of bonds that are primarily responsible for holding molecules together. We have covalent bonds, ionic bonds, and hydrogen bonds. We'll take just a moment now to explain each of these three types of bonds. Covalent bonds are formed when two atoms share electrons. No electrons are lost, none are gained, but two atoms simply both claim the electrons and treat them as if they were their own. So we've just learned about the octet rule, and we learned that each atom wants to have 2 electrons on its first shell and 8 electrons on its second shell. So when two atoms share electrons, then each of them consider themselves to have a full outer set of electrons because they're both counting those electrons. So if we look at some examples in this particular slide, we see methane. And so methane is, as the pointer is indicating, is a molecule that consists of a carbon with 1, 2, 3, 4 hydrogen atoms bound to that carbon. Carbon has an atomic number of 6. This means it has 2 electrons on its first shell and it has 4 electrons on its second shell. Hydrogen has an atomic number of 1. This means that it has 1 electron in its only single shell, the only shell that it possesses. So what we see is that each of these hydrogens needs 1 more electron to have a complete outer shell. Carbon needs 4 more electrons to have a complete outer shell. It has 2 shells, and so it needs 8 in that outer shell. Hydrogen only has 1 shell, and so it just needs 1 electron. And so each hydrogen shares 1 electron with carbon, meaning that each hydrogen now is content. It has a full outer shell. Carbon is sharing 4 electrons with these 4 hydrogens. It needs 4 additional electrons, and so now it considers itself to have 8 electrons in that outer shell. It has 4 that it originally possessed, and then 4 that it is sharing. And so that's a brief overview of covalently bonded molecules, or covalent bonds. Covalent bonds hold many of the biological molecules that we'll talk about during the progress of this course together. We can have 2 types of covalent bonds. We can have what we consider non-polar covalent bonds, and we can have polar covalent bonds. In nonpolar covalent bonds, electrons are shared equally between atoms. This means that the electrons are positioned exactly in between the 2 atoms because each atom has an equal pull on the electrons. In polar covalent bonds, we have an unequal sharing of electrons. Electrons are pulled more closely to one atom or the other. We'll talk more about nonpolar and polar covalent bonds when we talk about hydrogen bonding in just a few moments. Ionic bonds are the second class of bond that we want to talk about today. Ionic bonds, interestingly, are formed when one atom gives up its electrons and another atom gains that electron that was given up by the first atom. So there actually is a transfer of electrons. Remember, electrons have a charge of -1. This means that when an atom gives up an electron, it gains a charge of +1. And when an atom gains an electron, it gains a charge of -1. We call these charged atoms ions, and the bond that holds 2 ions together is referred to as an ionic bond. You're probably aware of the fact that opposite charges do attract, and in the case of ionic bonds are always formed between one positively charged ion, referred to as a cation, and one negatively charged ion, referred to as an anion. So perhaps the most common example of ionic bonding in our world would be the bond that's formed between a sodium atom and a chlorine atom. And so if we look at sodium, shown on the left-hand side of our diagram here, indicated by the pointer, we see that sodium has 2 electrons on its first shell, and it has 8 electrons on its second shell, and then it has 1 lonely electron out here on its outer shell for a total of 11 electrons, and therefore it has an atomic number, as you know, of 11. If If we look over here at chlorine, we see that chlorine has two electrons on its first shell. Chlorine has 8 electrons on its second shell, and then chlorine has 7 electrons if you'll count those on its outer shell. And so what happens in this particular case is as follows. It's not likely that sodium would ever be able to gain 7 electrons and fill up this outer shell. And so sodium gives up this electron, in the single electron in its outer shell. The electron moves from sodium to chlorine, and if we look over here on the right hand side of the diagram, we see that now sodium is content because it has a full outer shell of electrons. It has given up that 1 electron in the outer shell, and that shell is now gone. And so now sodium only has 10 electrons. If we look over at chlorine, we see that chlorine has gained that electron that sodium gave up. And so now chlorine has a total of 18 electrons. And so sodium has given up an electron, therefore it has a charge of +1. Chlorine has gained an electron, therefore it has a charge of -1. And so these two atoms are now charged. We refer to them as ions. Sodium has a positive charge, chlorine has a negative charge, and they stick together. And so this is an ionic bond. Sodium chloride, as you realize, is common table salt. And so the crystals of salt that you're familiar with observing consist of millions of these atoms that are bound together via these ionic bonds. The last type of bond that we want to talk about is perhaps the most interesting, and it's referred to as a hydrogen bond. Hydrogen bonds are formed when hydrogen atoms in one molecule are attracted to oxygen atoms that are found in a different water molecule. And so the key to understanding hydrogen bonding is understanding the concept of polar covalent bonds. So let's take a look at a water molecule and explain why the bonds that hold water together are polar covalent bonds. If we look at our water molecule found in the upper right hand side of the screen, you'll see the familiar structure. We have oxygen indicated by the pointer here. We have hydrogen indicated right here, and another hydrogen here. The hydrogens are connected to the oxygen via these bonds that are referred to as covalent bonds. Now, to understand why these are polar covalent bonds, we need to realize that different atoms have different, different atoms have different degrees of attraction for electrons. We use the term electronegativity to describe how much pull an atom has on electrons. Some atoms tend to pull electrons to themselves, and we refer to those atoms as very electronegative. Other atoms have a very weak pull on electrons, and so these atoms are not very electronegative. In the case of oxygen and hydrogen, the two participants and the two components of water, oxygen has a very strong pull on electron, hydrogen has a very weak pull on electrons. And so this means that in the covalent bonds that are formed between oxygen and hydrogen, the electrons are not equally shared. Because oxygen has a stronger pull on those electrons, it pulls the electrons to itself, as you can see indicated in our diagram. The electrons located here, 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 and here are very close to oxygen and very far away from hydrogen. Now it's fairly easy to understand then at this point, if you understood what I just described, what polar covalent bonds are. Polarity refers to an object that has two different sides. The Earth is polar. It has a north pole and a south pole. And so if we look at this bond then, we see that the electrons are located on one side of the bond. This means that the side of the bond closest to oxygen will be negative, and the side of the bond that is closest to hydrogen will be positive. And so the two ends of the bond are not the same, therefore it is polar. If we back up and look at the entire molecule, then we see that just like we have two sides to the bond, one side that's negatively charged and one side that's positively charged, the entire water molecule has slight charges on either end of the molecule. This end of the molecule, the oxygen end, is slightly negative, whereas this end of the molecule, the hydrogen end, is slightly positive. And so not only is water composed of polar covalent bonds, but water itself is a polar molecule. Now this is what allows hydrogen bonds to occur. I apologize for that. We'll go back to this slide now. So we see, look over here in part A of this figure, that a negatively charged portion of one water molecule is attracted to the positively charged portion of another water molecule. And the bond, shown in yellow with a dashed line here, that connects this oxygen, negatively charged portion of this water molecule, and the hydrogen, positively charged portion of this molecule, is known as a hydrogen bond. So hydrogen bonds connect one water molecule to another water molecule. It's important to note that covalent bonds hold water molecules together, but hydrogen bonds form between two different water molecules. Hydrogen bonds are very weak bonds. If we look at the order of strength of these bonds, we see that covalent bonds are the strongest, ionic bonds are the next strongest, and then hydrogen bonds are the weakest. Interestingly, these hydrogen bonds give water a number of unique properties. Water has a high heat capacity. This means that you have to add a lot of heat to water before the temperature of water begins to change. This is because the first heat that's applied to water goes to breaking those hydrogen bonds that we saw in the previous slide. So you have to add quite a bit of heat so that those bonds break, and then the water molecules begin to move. And the faster those water molecules move, then the warmer the temperature of the water becomes. Water also has a high surface tension. This means that the water molecules stick together and they tend to exclude anything else that comes along. And so this means that insects, such as water striders, can make their living basically skating around on the top of water. Those water molecules would rather bind to each other than actually bind to the foot of the insect. Water is also an excellent solvent. This means that water can dissolve many different substances. We see this depicted here in the figures shown on this slide. We see sodium chloride and water shown above the diagram, or above the bottom of the diagram here. And then what we see is that water dissolves salt, sodium chloride, because the sodium, the positively charged partner in the ionic bond, is attracted to the oxygen atoms of water molecules, whereas over here we see that chloride, the negatively charged portion of the sodium chloride molecule, is attracted to the positively charged hydrogen ions of water molecules. And so the water molecules that surround the two partners in the ionic bond are referred to as spheres of hydration. So these molecules form these circles basically around the ionic partners, and they separate the ionic partners. And so this means that sodium and chloride break apart when they're placed in water, and we refer to that as dissolving in water.